All right, everyone. Welcome to my presentation on shadows. So we're going to step into the shadow realm. So first, what are shadows? Before we can really reasonably answer that question, we need to let's have a brief overview of where this is going to go. First, I'm mostly going to be referencing quantum invariants of knots and three manifolds by Vladimir Turaev, and also a short introduction to standards of four manifolds by Francesco Costantinos. As for the hand-drawn images, those are mine, and just to get this out of the way, the ones that don't look hand-drawn, someone else made those, and now you know who, so that way people don't yell at me for not citing my sources. We're first going to talk about two polyhedra and gleams, which are kind of prerequisites before we can talk about what shadows are. And then we can look at what we can do with shadows, basically the basic shadow moves, which are analogous to the Reidemeister moves. And then we'll look at how these pertain to links in particular. And so let's begin. So first, what are two polyhedra? I like to think of them as kind of like a higher analog of graphs because they act a lot like graphs, but they're not technically graphs. But first, it's not what we usually think of when we're talking about polyhedra. We're not necessarily talking about cubes and icosahedrons and other things. What we mean is something more general, a compact simplicial space. And so we say that X is a simple two polyhedron without boundary if every point of X has a neighborhood homeomorphic either to R2, to the union of three half-planes in R3 meeting along their common boundary, so kind of like a book when you grab by the pages and leave the ends to flop out, or the cone over the one skeleton of the three simplex. You can see which one's the odd one out. And then we could also define one with boundary if we also include the half-plane, the positive real numbers. So, and I'll have pictures of what these neighborhoods look like in the next few slides. And then also we could take the union of three copies of the positive quadrant. And how this differs from this second region here is that there we're kind of concerned with something along kind of like the spine of the book, if you remember that analogy. But over here we're kind of concerned with something like the tail of the book here, along what these look like. So a picture to follow. So first, polyhedra without boundary. Let's get up close and personal with them. Here's us getting up close and personal with two polyhedra without boundary. So things in the type 1 is things that are homeomorphic to R2. This is what I was talking about, kind of like looking with the book open. And then while I would show a picture of a cone over the one skeleton of the three simplex, that is kind of ugly to imagine. So often you'll see it presented this way because this allows you to see where all the components are much nicer. So it's equivalent here. And for the sake of simplicity, I'll be referring to them as type 1, type 2, and type 3 throughout the discussion. And now, let's get up close and personal. But this time, let's respect their boundaries a little bit more. And so here's what those other two regions look like. We're talking about the half plane, but instead we're sitting on the edge instead of being up inside the rectangle area. And then instead of being on the spine of the book, we're at this little corner here. So those are kind of the regions of these two polyhedra. Are there any questions before we carry on with this? Yes?
So, I know you didn't want to draw it, but what is a cone in this context?
By a cone, we mean that we, what I mean by the exact definition, I don't know off the top of my head, but if we take, the one skeleton of the three simplex, we imagine some point in the middle. I want to connect everything on the edge to that point, and then do that for all of the edges.
Okay.
And so you get kind of like this funky Y-looking shape with an extra branch.
Okay.
Which is another way you can visualize that type 3 region is by taking like a 3D Y and gluing it to some disk kind of thing and twisting it around a little bit.
And that point has to lie on one of the edges.
What point has to lie on one of the edges of simplex?
So you said you draw a point, you connect all the things.
Oh, yes, living inside the simplex.
Okay, but you can pick any point inside.
Right, you'll get the same sort of results, I think. Someone who's more knowledgeable about this can correct me if I say something silly. Let's see, other things before we carry on with this. Am I forgetting anything? I don't believe so. All right. I'm sure it'll occur to me later if I forget something. So we also give names to these parts of the polyhedra. So for instance, the points in X that have neighborhoods of type 1, remember those are the ones homomorphic to R2, those form a surface which we call the interior of X, not to be confused with your usual interior. It's slightly different. And the connected components of the interior are called regions. Some more jargon is those which have no neighborhoods that are of type 1 or type 4 are denoted the singular components of X, and those which have no neighborhoods of type 1, 2, or 3, so those boundary ones component are reasonably called the boundary of X. Oh yeah, sorry. Can I go back? I hope this thing allows me to go back. Why won't you let me go back?
I think it's because you're recording the stuff.
That's probably it. I'm sorry, but do you remember what it was that you were looking for?
I just wanted to absorb the information on that slide.
For
Int X and sing X is what, and that sort of thing.
Right. So like in this picture here, one thing you might see is that, so what I've made, this is a non-trivial example of a 2-polyhedron. A trivial example for 2-polyhedron would just be any 2-manifold, because all of its points have a neighborhood homomorphic to R2. But you can get a little funky and see we can take S2 and we can glue 2 disks to it, one along the inside, which is the red disk here, and we can glue another disk along the outside, which would be that blue disk. And I made a point to glue them differently from one another, which will become relevant later.
So what would int be in this case, and what would sing be in this case?
Yeah,
Whatever the third bullet point was.
The third one was the boundary. Okay, so the interior would be like these orange slices of the sphere. That's one example.
Yeah.
And also the interior of the red disk and the interior of the blue disk.
Okay.
Those would be the regions of this polyhedron. The singular components would be the edges and the vertices here.
Okay.
So that'll be this boundary of the red disk, the boundary of the blue disk, and
I think that's it.
I think that's it. Yeah, and then or is that just the boundary?
No, because boundary.
Yeah, and also the vertices, which is where the blue, red, and blue disk, red disk, and the sphere meet here and back here.
Yeah, but I don't think that's the boundary. I think that's.
No, those are the vertices. Yeah.
Yeah.
So that's a quick example of looking at the anatomy of this 2-polyhedron.
Cool.
Oh yeah, and going to why I called this kind of like a higher dimensional analog of graphs is because they have a sort of combinatorial structure, which we'll look at in a second. Notice that I called these points F, E, and V. That'll be relevant later. But as you can see, this really is a 2-polyhedron because things in this white region do look like R2. Things along this component here look like that sort of book together. That's where the red disk is, and then those are the 2 parts of the sphere on either side. And that V component here, that's what it looks like when we zoom in. So, and also, oh yeah, that's right. I could have picked the boundaries because this has no boundary. This doesn't have boundary components, I don't think.
Yeah, that's why.
Yeah. Okay, very good. Look at me confusing myself.
We figured it out.
We figured it out. This actually gives us a nice sort of combinatorial structure of the graph. As it turns out, when you take the 2-polyhedron and subtract the regions, you get a union of 2 things. You get the singular components and the boundary components. And they form a graph in the sense that it's a 1-cell complex. In the case of the previous example, we had 2 vertices and 4 singular components, which are those edges, the ones with the disk meeting along the sphere here and the blue disk meeting along there. And so this gives a graph with 2 vertices and 4 edges. And what's really cool is that this encodes so much of the information of the polyhedra that we can go in reverse. If we take this graph and then glue disks along any 2 pairs of regions, we get the original polyhedron. Not all of them you can do this. Sometimes you have to specify a certain topology for the disk you're gluing in, or you can't just glue in a disk, you have to glue in some other surface. So this is a special case which we call standard polyhedra. I won't be referring to them much in here, but just some are nicer than others.
So does it depend on how you glue the disks in? Maybe you just said this, but I can see like a bunch of different ways to glue in circles onto those things, like maybe like a small one and then a big one on the outside, or like a left one and a right one.
Yeah, that's sort of the caveat here. Like the standard, we should I don't recall the exact definition, but I believe that for standard they require a nice parameterization of like gluing the disk in normally. Like you don't get any twists in the disk, I don't think.
Okay.
If that makes any sense.
It kind of does.
But you're right, yeah, like this really does depend on like how you glue the disks in.
Okay.
So there are some choices to be made.
Okay.
But the overall structure is at least preserved.
Yeah.
Okay, so what else are we looking here? So now that we've looked at what two polyhedra are, now we can get into the fun stuff of gleams and shadows. So first off, what are these things? So we pick your favorite abelian group. A shadowed polyhedron over A is a orientable, simple two polyhedron such that each of its regions is endowed with an element of A. And what it means for a polyhedron to be orientable is that we since each of these regions is, we just pick an orientation for each of these regions. Like we can induce one by picking one orientation on one region and just kind of extends to the rest. And we call this association the gleam. And before we get into doing some stuff with the gleams, there's some. So one example of a gleam would be what's called the Z mod 2 gleam. I was hoping to show this with a picture of our previous illustration, but apparently I cannot go back, which is sad. So I'll just draw on the board what's going on here. But so what we do for the Z mod 2 gleam is that you can imagine taking our polyhedron that we had initially. So we had that sphere. And let's say I pick this little orange slice here and call that, what did I call it up there? Let's call it y. And so the boundary of y is going to be this sort of path along this polyhedron here. And what I can imagine doing is placing my hand along one of the walls when you're standing on the edge of y, and just walk along and walk along. Eventually I come to a vertex. At that point I have a choice to make. Essentially what I do is just pick one of the walls that's, so when I get here, one of the regions does not touch y. It only touches the outer corner. The other two touch y in some other capacity. So I just pick any of the other regions that still touches y other than at the corner. So in this example, like this orange slice opposite of y only means y at the corner. But these other walls touch y. So I can just pick one of those. And so I pick one, continue my path, walk along, and I keep making these sorts of choices until eventually I get back to where I started. So what's going to happen is that my hand's on the same wall as when I started, or it's on a different wall. So essentially what this boils down to is either the region y, when we remove it from the polyhedron, the remaining thing collapses over a cylinder or over a Mobius band. So a cylinder is if you came back to where you started, Mobius band if you came back and your hand was on a different wall. And so if we collapse over a Mobius band, we assign it the value of 1, otherwise we assign it a value of 0. And so this is one nice choice you can do. This is one that also shows up a lot. Another common gleam you'll see is the half integers. So we'll take the integers and also include the halves, 1 half, 3 halves, 5 halves. Why exactly that is, I have not looked deep enough into the literature to see why, but that is something you'll see frequently. Oh yeah, and by Costantinos maze-walk illustration is that thing I was describing here. Here's the technical way to do it above, and then imagining with your hand along the wall is a sort of intuitive way of how you might do the Z mod 2 gleam.
Yeah.
Cool. So some remarks on gleams is that it's useful to think of them more as like concentrated in different areas of the gleam, of the region. So we can imagine that maybe it has a value of A1 over in this part, and then A2 over there. And so the gleam of y is really just the sum of all of these concentrations. When we get to the shadow moves, we'll see why this is a sort of useful thing to do.
Why is A1 different from A2 if it's part of the same region with the same boundary?
What I mean is that you want to pretend like the gleam can be broken up. So the gleam of y really is the sum of these elements. We'll call it some element big A, or not big A, let's call it
Okay,
B.
so we're breaking it up first and then like assigning different weights in different areas or something?
Exactly, yeah. Because sometimes when we do shadow moves, you might cut out certain parts of the region.
And that might affect the gleam?
Yes, you want to be able to keep track of the gleam in a reasonable way.
Okay.
So that's when we imagine you can kind of break it up a little bit.
Okay. And so, because the gleam is either 1 or 0, right?
For the Z-mod 2 gleam, there are other choices you
for
can.
Z-mod 2, okay.
Oh yeah, I realize that would be confusing there. For Z-mod 2, this doesn't make a lot of sense.
Okay.
I guess if you do 1s and 0s, that could still work.
Okay.
But remember, A could be any abelian group. The Z-mod 2 gleam was just one type of gleam that you might see thrown around.
Okay. I think I'm good with that diagram.
Okay, good. Any other questions before we proceed? All right, so yes. Oh, first I'd probably clarify why the gleams are important. So when we assign these gleams to the polyhedron, we call it's like the shadow polyhedron. These are the shadows. And so now, when we manipulate these regions, we now get the shadow moves, or as I like to think of them, Reidemeister's nightmare. So we have 3 of them. The first one is P1. So what we do is that we are at the vertex, and we take that bottom half, and we kind of change the way that it's glued to the rest of the polyhedron. So we kind of get this new disk sort of region shoved in where the vertex was. And we assign that a value of omega. And the result of this is that this also changes the surrounding gleams too. So what used to be A1 over here is now A1 minus omega. Which I guess is kind of an arbitrary choice, but the reason why I think why these moves are defined this way is that we want them to be invertible. So if you imagine undoing this thing where you get rid of that omega region, things will kind of connect in such a way that they'll want to cancel out and give us the sort of total gleam. And so this is kind of the choice that makes sense if we want P1 to be invertible.
So they still add up to what they're supposed to add up to, both base-wise and, well, maybe not.
P1 is sort of the exception. P1 does change the gleam of the region.
That's what I was going to say. It's like that top leaf right there. It does seem like it would change because it's 2 negative omegas and 1 positive omega.
Right.
But the other ones don't change?
They don't. So for example, we get new disk regions whenever we do P2 and P3. The first disk region, we push over this 1 stratum, by which I mean an edge. But that gets assigned a gleam of 0. And so nothing really changes. And the same thing down here across the vertex.
So we're just assigning it a gleam of 0.
Right.
Okay.
And this assignment allows us to do nice algebraic things with them. In fact, that particular element omega turns out to be really important to where sometimes we classify shadows according to whatever that omega is. Because it's the only move that actually changes the gleam, P1. And as you can see, they kind of look like the Reidemeister moves. Think about it. P1 looks kind of like untwisting and twisting. P2 looks like a push. And P3 looks like that weird thing where you pull 1 strand across the other. Just taking place in... Oh, that's the other thing. So this is often done in 4-dimensional space. So sometimes where you see intersections, there aren't actually intersections. Like P1, for instance, we can't really draw that in 3 space.
Yeah. And I was going to say P1, you said can't be embedded in R3, so this is sort of like a schematic.
Right. This is our kind of best approximation of what's going on here. Intuitively, you just want to think we just glue a new disk in and assign it a gleam. So in the case of P1, we glue a disk in where the vertex was, assign it a gleam of omega, and then change the gleams around it accordingly. P2, we put the disk in across that 1 stratum and assign a gleam to 0, and the same thing with P3. All of these moves are invertible.
Yeah. So you can go
backwards.
to the right or to the left.
There is sort of an issue with inverting P2 though. Because you might notice, like, okay, so what if over here, what if A4 has like 1 orientation, whereas this one labeled A6 has a different orientation? When you do the reverse, now these 2 are part of the same region, and so you might not have a nice orientation. So for P2, we use the mathematical strategy of sweeping it under the rug, where we only consider it to be invertible when it makes sense to do so.
Okay. Cool.
So we don't break orientation. Alrighty. So just some other comments on these shadow moves is, first, they take place far away from the boundary, by which I mean they take place in some neighborhood that does not include the boundary. So the boundary remains unchanged by shadow moves in general. 2 regions can look distinct on the local level, but be part of the same region on the global scale. What I mean by that is, let's say we had this sort of vertex region here. So this top vertical plane might look different from the bottom one, but it may be that when you zoom out, they actually are part of the same region. And so it's important to remember that these happen on the local level.
Okay, so like that might twist back to itself.
Right.
Like kind of like a, not even a Mobius band because it doesn't line up there, but like a half Mobius band or something.
Right. And so any changes in the gleam up here may actually affect the gleam down here.
Okay.
And like I said before, each of them have an inverse. Like I said, P2 sometimes doesn't, but we just pretend that that's not. Oh, we just ignore it whenever it doesn't have an inverse. And this also induces an equivalence class on the polyhedra. So two shadowed polyhedra are equivalent if we can get one from the other by a homeomorphism or a sequence of shadow moves. And these equivalence classes of polyhedra are what we call the shadows over the abelian group A. And so that's the quick rundown of shadows. Are there any questions from you all? All right, let's.
Is there any way you can give an example on equivalent shadow?
Anyway, I can give one. Well, I guess like a sort of dumb example would be is that I
Love them.
I love dumb examples. Yes. So I can take the sphere with a zero gleam and then map it to this cube, also with a zero gleam. And so we get there by homeomorphism. Or if we, I guess a non-stupid example is if we take our weird sphere with two disks attached to it. One shadow move that we can do is that we can do P2 on if we do P2 on this sort of edge here. What would that look like? So up here we have something that looks like, actually no, wouldn't be.
P2 would need
Yeah, we go with vertex. Yes, we can do P2 in this area here, where we push this top disk over the vertex here. And so this kind of changed the way that this is glued to the polyhedron, so now the disk meets it in a different place.
And so with the weights being in whatever places we want, that might change not the overall gleam, but the like local kind of.
Right, like a.
Is that why we're doing it? Because that's like a homeomorphism of each group.
Yeah, where is it? I guess no, we pushed that with the vertex, so that's P3. I was not prepared for that question, so I'm scrambling a little bit.
Sorry.
That's all right.
I'm giving you a hard time, but.
No, that's all right. But yeah, you're right. Like any sort of
like.
like, if you imagine take this example we had earlier, doing P3, you push it over the edge. It'll change the way that's glued. Or we can do P2 to this top disk over here. It'll push it through so where the disk kind of has this weird self-intersection sort of thing. But so we made a new region, and so it is kind of distinct from the original one.
So,
but like we can still do shadow moves to get from one to the
So
next.
kind of like this. Like if you had a thing like this, and like this.
Yes, like with a weird disk kind of glued over the top.
Yeah. Okay. I think I see.
I think.
I think I see that.
Are there any objections to this example? I guess it's fine otherwise. No, it's not. Okay, so now we can talk about the fun stuff because we're not in link theory people.
Woo!
For the most part, I guess. We have some TDA and other things going on here, but
Yeah.
I feel like the last few discussions have been almost entirely about knots. But now let's do links. I'm not attacking anyone, especially not Ethan. First, shadow links. So what we can do is we take our shadow polyhedron, and then what we do is that we do a shadowed system of loops over it. So we just take our polyhedron and draw circles in the shape. Well, I guess they could also be a figure eights and other things, as long as they're, loops. And so we call this a generic system of loops. There are some conditions on what you can do this loop. So first, they can only have double transversal crossings and self-crossings lying in the interior. So double transversal, by that we mean that it if two loops are sort of crossing, if it goes in, it comes out. So transverse here. And then also, it doesn't go over the boundary, first of all. or if it has a self-crossing, I mean, we can't have like this sort of thing happening and then, oh, there's an edge. If it's got to have self-crossing, it's got to do it entirely within the interior. And let's see. And so we call this system of loops shadowed if we first assign an element of the abelian group to each of the loops, which we call the pre-twist of the loop. And notice that L creates a new each loop creates a new region. And so this space inside the loop, we give that an element of the abelian group called its gleam to stay consistent. And in order to play nicely with the rest of the shape, we want the gleam of this system of loops to equal the gleam of the region that contains it.
Don't move on yet, sorry.
Which, by the way, the system of loops does not need to be entirely within one region. It's just that the region, if you have parts of the loop in one region, the sum of those gleams has to equal the gleam of that region that it's contained in. Any questions with these definitions or things I should elaborate on?
1 second, I'm on the last bullet point.
Sure.
Okay, cool.
Cool. So what can we do with these links? Well, first off, we can actually make new shadow polyhedra from these links, the cone and the cylinder over these. And they are exactly what you sort of expect. So we can take our loop here, and then we could glue a cylinder along the loop. Of course, we pick some parameterization for this. That makes this work nicely. Alternatively, we can take this thing and cap it, which gives us the cone, accordingly. These two happen to play nicely with each other. So for instance, if you have the cylinder over polyhedron, there are these things called shadow operations where you can obtain new shadows from other ones, new shadow polyhedras from other ones. And you use the operation called capping, where you just glue disks to all of the cylinder components. And that'll get you from the cylinder of the system of links to the cone. And that makes proving things a lot nicer because if you know one, you can kind of get the other. And as you can expect, we also have shadow link moves, although they are a lot more elaborate than just the regular shadow moves. So there's 8 of them, and we consider 2 shadow system of loops to be isotopic if we can get from one system of loops to the other by using these shadow moves, or by just sort of ambient isotopy in the polyhedron. And like with the case with shadow polyhedron, equivalence classes over these are called the shadow links in the polyhedron. What's going to happen next, I'm going to show you a series of photos of each of these moves. Just so you are aware of, since these are a lot more elaborate, I just want to make clear what the thing is going on here. The bold lines represent the links, so you can distinguish them from the things that are drawn in the polyhedron. You'll see 2 different groups of elements. If they're in a box, those denote the pre-twist. Remember, those are the group elements assigned to the loop itself. And those that aren't in there are the gleams of the regions of the polyhedron. And as before, not all moves affect these pre-twists. So for example, only S1 and S4 affect the pre-twists. Analogously, the shadow of P1 only affected the gleam. So let's look at these. So here are the first 3. These take place all within the same region, so we don't need to draw the surrounding neighborhoods. And they look a lot like the randomizer moves, which is pretty happy and joyous, if you ask me. And I'll just take a few instances for you all to look at them for your viewing pleasure. Now we'll move on to the next few. Here's S4, S5, and X6. These take place across a one stratum of the polyhedron, and so that's what we get there. And then our next group of moves takes place across a vertex, I think.
So.
Oh, yes. Sorry.
No.
Oh, never mind. They don't. I was off.
This one applies as well. So I noticed you don't have boxes for like every single strand. So you're not maybe you are assigning an element to those strands, but is it just that like it doesn't change is why the boxes are?
Right, because each one does have to be assigned a pre-twist as part of the definition of a shadowed system of loops.
Yeah.
It's just that only moves S1 and S4 affect the pre-twist, and so those links we need to record it for the sake of simplicity.
Okay.
And we'll come to find that in later diagrams I'll be drawing, particularly for a proof of something I want to show you towards the end. We're not going to draw everything because it gets really weird to imagine, especially because we like a lot of this to work in 4 dimensions.
Yeah.
So, and then I don't know if you can see it very clear here, but there's kind of like a break in these lines on S7. And that's because that strand takes place in the back. It's on that bottom plane. So it's not like one's overlapping the other.
So it's like a dash line.
Yeah, it's a dash line to show you that it's taking place in a different half plane. Not that one's crossing over the other necessarily. Except for the intersection on the right where they do touch each other. Okay, shadow links. It is here that we arrive at a happy and joyous theorem, which is that if you have 2 shadow system of loops that are isotopic, then the shadow polyhedron that you get from them, the cylinders over them, are shadow equivalent. And the same also holds for their cones. And so this is like, I think it's pretty cool that we now have this.
Nice.
It's a nice way to link the 2 together, pun not intended. So how do we know this? What we're going to do is we're going to look at this sort of case by case. As it turns out, for most of them, it's pretty clear what the shadow move is. I probably should have labeled what each of these moves are. I forgot to include that. But if you go through and look at the diagrams for many of the, oh yeah, I have written up there. For moves S2, S4, S5, S7, and S8, when we attach the cylinder components to each of them, you can pretty easily see what the corresponding shadow moves are. And so those are the pretty nice cases. I do realize there's an issue with the first one where we didn't say you could always do P2 inverse. But for now, we'll just sweep that under the rug, since it's sort of an introduction to shadows and we won't get to the technical details. Are there any questions about this first part of the proof? Okay. So here's where we kind of compromise the visual intuition a little bit. S3 and S6 aren't as nice. It's not as easy to see them as shadow moves. But what we want to do is kind of get rid of some of the noise so that we can see them as shadow moves. Remember that S3, you have, I forget exactly what this looks at the top of my head. I have the book here, actually. The point is, we can just zoom in on the intersections of these moves. And this is what you're seeing here is kind of the zooming in. So the vertical planes here correspond to the cylinder components of those intersections.
So is this move S3 or is it?
So this right here is S3.
Okay.
You can do S6 analogously.
Okay.
Right now we're just focused in on like a tiny neighborhood of these moves. In fact, if I put up S3, I can show what I'm talking about. Okay, yeah, so S3 is going to be this thing right here. So we move that, where we take this back one and flip things over. We have this one. And so what we're doing is kind of zooming in on the crossings and looking at the cylinder. So what happens with this other strand, and so this is the other strand, what happens as we push it across here. So this is the black strand that we're looking at. And the vertical planes are the cylinder components of this intersection. And so when you look at this, you realize it's just a composition of the shadow moves, P1, P3 inverse, P3, and P1 inverse. And so since they're equivalent by a series of shadow moves, that means that S3 that proves that case. And the same thing for S6. I'm not sure if you saw with S6, it's a similar story going on there, only this time we're doing it across a one stratum, so we have something that crosses along like this. And so we just need to zoom in on the intersection here and look what's going on when we cross the edges. And then that leaves only S1. And this one is just weird. I don't think that I don't remember if in this case the vertical plane means anything significant. I think it's just that it's a non-trivial way to show it. It's not trivial to show, but this is what you can do. Doing shadow moves on the surrounding regions changes this so you can accomplish S1 through a series of shadow moves. Any questions there? But yeah, that's all 8 moves. So we have proven our theorem there. Proven in quotation marks. If you're hungry for more, there is a lot more that can come through this. You can have surgeries on shadows, operations on shadows, shadow graphs, shadows of 4 manifolds. There's a whole bunch of things you can do, as Bubba so very clearly states here, as you do with shrimp. And so if you're interested in looking more into this, some of the big names I see a lot in this sort of area are Vladimir Turaev, who happens to write this book, which I'm going to return to the library if you want to take it there. Francesco Costantinos is another one, and Dylan Thurston are some of the names he's thrown out a lot. That pretty much covers everything here. So we're now out of the shadows. Presentation's over. You were safe. Are there any questions from you guys?
I asked all of them during the presentation.
Which I appreciate you did. All right then, that's pretty much everything. Thank you.